Welcome to BKW Physics. I'm Mr. McConnelly. We're going to learn a new physics equation today. I want to start with a concept that you're already familiar with. If you have a velocity time graph and your data looks something like that, your graph looks something like that, where your velocity is increasing, you know that this means you're accelerating, right? This slope gives us acceleration. And if I had you find the area underneath here, you know that that would give you distance. So in this particular situation, the way it's set up, the way I drew this graph, I could break it into, say, a triangle and a rectangle, these two shapes right here. If I find the area of the triangle, and I add it to the area of the rectangle, it'll tell me the distance. This is, we've already done this. You know this. Well, I can kind of develop an equation by doing this, because if I label this like initial velocity and final velocity, and this is 0 here, I can start to develop an equation. Long story short, because I'm not going to go through all the process of doing that, if I use this concept, I can get an equation that looks like this. D equals 1/2 VF plus VI times t. It's an equation. It'll help us find the distance when we know the initial and the final velocity and how much time you've been accelerating for. Pretty straightforward. Now, there's another equation that you've already been using quite a bit. It's the VF equals VI plus AT. And what I propose is, what if we combine these two? What if we took those two equations, and in fact, I took the VF, or I took this stuff right here, and I plugged it right in there. Okay? What I would get, since these are two correct equations, when you combine equations, two correct equations, you'll get another correct equation. So, again, the long story short, because I don't want to go through the math of doing that, that's not really important for you to know right now, you get D equals VIT plus 1/2 AT squared. That, I put a square around because that's in your reference table, and that's the one we want to focus our attention on today. Don't worry about the details, how we got there, just realize we used a true concept that we already knew, an old equation that we already knew, and we combined them to get a new equation that we haven't seen before. So this equation says that distance is equal to the initial velocity times the time plus 1/2 the acceleration and the time squared. So we haven't used one with a square yet. It's a little bit different. We'll see how it works here in a second. So if we can pan on over to a problem that I have right here, we can focus in on this problem 17 here, okay? Focus in on this problem 17. Is it clear enough in the camera you can read that?
Yeah, you good.
Okay. So it says an airplane starts from rest and accelerates at a constant 3 meters per second squared for 30 seconds while leaving the ground. So if I'm just kind of pulling my information off of this, starts from rest, what does that mean? I know the initial velocity. Constant acceleration of 3, I know the
acceleration.
And 30 seconds, I know the time. I'm looking for displacement. Hey, this seems like a perfect way to use our new equation, and we could throw the numbers right in. I'm not going to, okay? I'm not going to because I want to show you a little bit more of a complex equation here. So first of all, let me figure out how to erase. Is that it? There we go. And let me back up to another problem in this book, which is similar in nature. My bad. There we go. This problem number 13 right here. Let's focus our attention on that one. It says a race car is traveling at 44. It's uniformly accelerated. So 44 is its what? Initial velocity, right? It's accelerated they don't tell us the acceleration. Okay. Then it accelerates up to a velocity of 22, so that'd be a
Negative acceleration.
that's a okay, but don't worry about it is a negative acceleration. I agree with you. Nice job. Way to jump on that. But this is a final velocity, and that's a time because it's 11 seconds, and they're looking for a distance. So this seems a little harder. And what I'm going to do, I'm going to leave that up, but I'm going to have the camera spool over here again. And just got to find my eraser. There it is. And we're going to kind of work through this because this is a much harder problem than the first one I pointed out to you. So I can still see the problem even if you can't. And I'm going to write down some of the givens. I'm going to write down that there's an initial velocity of 44 meters per second. And there's a final velocity of 22 meters per second. This happens over a time of 11 seconds. And we want to know displacement. Now when I first start looking at this equation and looking at these givens, there's a little bit of a disconnect here. It doesn't seem like that equation is going to work for me, does it? Because I have time, great, so I got those two things, check. But I don't have the acceleration and I don't have the distance. So, what to do? Well, here's what I got to do. The reason I picked this problem is because it's pretty hard because you got to do two steps. The first thing I'm going to do is I'm going to realize that, yeah, I definitely want to use this equation in the end. But I don't have the acceleration, so I have to do what's called a little side problem to get the acceleration. And what I'm going to do is I'm going to go back to the old concept of acceleration. Remember, this was also a reference table equation. Acceleration is change in velocity over time. And remember, that means final velocity minus initial velocity over time. Let's plug in the numbers. Final is 22. Initial is 44. And as Zach so astutely pointed out a minute ago, since those numbers are arranged the way they are, that's going to give us a negative acceleration. And the time is 11 seconds. So what do we end up getting for our acceleration here? Got it?
Negative 2 meters per second.
Negative 2. Negative 2. Meters per second squared. Good. Can you see that low? Still picking it up?
Yep.
Okay, good. So we got negative 2 meters per second squared. Now I can finish off the problem because I found my acceleration and I can go back to this equation because all along, remember, I was trying to find displacement or distance. So I need my initial velocity again, 44. I need my time now, 11 seconds. My acceleration I just found a little while ago to be negative 2 meters per second squared. And now I got to take the time on the end and square it. Now some physics students have trouble with this because they forget their order of operations, okay? You can't just try to, I know a lot of you like the calculators where you can plug everything in on the screen, and I like them too, they're nice. But you can't just plug this all in with all helter-skelter, willy-nilly. You got to pay attention to your order of operations. You got to know that things need to be squared first, then multiplied, and then added to the other terms. So you kind of, if you think of it, you got to take this side and add it to this side as the very last step. So if you're putting it in on your calculator all at once, you got to be real careful with parentheses. I recommend that you do it with a few little steps. Square first, multiply, get an answer. Do this side, get an answer, add them together at the end. Then you won't make as many mistakes. You do what you want. Anyway, bottom line is, if you're cranking this out in your calculator, you will get 363, actually, not 36, 363 meters of distance. So to answer the question that was asked, it says a race car is traveling this fast with this situation. How far does it go? What's its displacement during this time? It will displace itself 363 meters. And that's the use of our new equation for today, physics.